Hey, I'm Yuri Dzubin, a conversational backend developer at Master of Code Global and Glia, and this video demonstrates my try to implement a context-enhanced question answering setup using only open source components, which can be run locally. In the earlier video, I presented my pet project built using the OpenAI Pinecone stack, where OpenAI Embeddings endpoint was used for generating vectors. Pinecone was used to store the vectors and corresponding text and to do similarity search for contexts. And OpenAI completions endpoint was used to generate answers based on the retrieved context. However, in some cases, using these services might not be possible. And one of the main possible reasons is security considerations. So some companies may be cautious and won't agree for their data, either for contexts or the queries, to be sent to the external APIs, especially taking into account the stories about potential leakage of internal data through ChatGPT. So I tried to construct the setup with an embeddings model, vector storage, and language generation model, which could be run locally. Also, this is my first acquaintance with LangChain framework. So this proof of concept is a pet project, which is a compilation of examples from LangChain documentation and similar projects of other developers. It was implemented as a Jupyter notebook, as a Google Colab. Please see the link to the notebook in the video description. For generating vectors, the HuggingFace model, all MPNet base version 2 was used. Vectors were stored in the FAISS database, and for language generation, the model GPT4ALL was used, the 7 billion parameter version, available as of April 2023. So let's go through this notebook. It's composed of several sections. First, we prepare and check each of the components of this setup, and finally we combine and run them all together. This notebook uses a default Google Colab runtime without GPU. And first, we will start from preparing our language generation model. But before I will mount my Google Drive, we will be storing all our assets there, including the language generation model file, the index with our contexts, and the embeddings model file. So we've got our drive mounted, and here are different files which I already saved there, but I will go through those steps again. So next we will prepare our language generation model. As I noted, I was using the GPT4ALL, the 7 billion parameter GPT4ALL model. So the original model file called GPT4ALL LoRa quantized bin didn't work in this Colab, and I needed to convert it following some examples found on the internet. And then I've got this converted file, which I stored in my Google Drive, and I am mounting it each time. So these steps marked 1A need to be run only once if you do not have this converted file. And to convert the model, we first need to download the original file. Then we download several dependencies, and this may take some time. And for me, it did not work like from the first try. One of the files failed to download. However, I was able to cancel running this cell and rerun it, and it succeeded finally. And then this script is run, which generates the converted file, which I called GPT4ALL LoRaQ converted bin. And this cell copies the generated file from the storage of the Colab to our mounted Google Drive. So here it is. If you already run this 1A section, then and you have this converted file stored somewhere, we will just set the path to this file, and we are able to test the model. As I noted, this Colab is using this LangChain framework for creating applications powered by language models and other tools. For this, we will install LangChain and also the package to work with our model. We will import several dependencies. We will prepare our model, passing the path to our model file. While it is running, let's look further. Then we will create a prompt using this prompt template, and then we will be using a chain to run our model with a given prompt. Okay. And we are ready to run our model. Let's see how it works. So, while it is running, let's try running this query on this same model locally on a M1 CPU MacBook. So this is done quite easily. One needs just to download this file, and then to put it to pull this repository, to save the file into the chat directory, and then to run this command being in that directory. Here is our file. The model loaded. Hello. I don't know what this is. Running. So let's try running this. As we see locally, it is responding quicker, though not really relevant. Okay, so after 4.5 minutes, we've got this answer. Let's maybe try something different, something simpler. Okay. Next, we need to prepare the contexts, which will be passed to the model together with a question. In this POC, I used a PDF document with a free course on JavaScript from the site goalkicker.com. So it's a quite big PDF. Could have chosen something smaller, but nevertheless. So for this, we will run this section. We will need LangChain, a package for working with PDF files, and we will import a PyPDF loader from this LangChain document loaders. I have this book stored in my mounted Google Drive the file is called JS4Profs PDF. So here I'm setting the path to this book. Then we instantiate a loader using this PyPDF loader from LangChain package and pass the path to the file. And here we load the contents of the document. It will be an array of document items. So each with keys page content, with the content of a page, and then a metadata which shows where the file is located and the number of the page. And if we run this block, here at the end we will get the number of pages. So this loading takes some time. I did that earlier. I won't do that now. Here is the print out, and at the end we got this number, that is, we have 490 pages. Our model GPT4ALL has a quite low token limit. Mine has 512 tokens, so probably not each page will fit into that limit. And in addition, we need to pass the question and to get the completion. So we need to split that information. For this, we will use a recursive character splitter, text splitter, from text splitters of LangChain package. And for the sake of this POC, we will be splitting into quite small chunks, 250 characters length. So it will count by characters, and the chunk size will be 250 and no overlap between the pieces. After running this block, we will see that this document will be split into 4,262 pieces. Next, we need the embeddings model, which will generate vectors for our text pieces. In this POC, I used this HuggingFace model all-MPNet base v2 with 768 dimensions. And if you do not have this model saved yet, you need to run this block once. And here again, I did that already. I have this model already stored in my mounted Google Drive. So what this block does, it installs sentence transformers package, and when it is installed, it automatically loads and caches this model. It's around 420 megabytes. After this model will be used from the cache. However, in case of a Google Colab, this cache will be cleared after the runtime is disconnected. So we want to save it to our persistent Google Drive, and also make it possible to use this model without downloading. So Here we download this model and we save it locally. Embeddings model save, and we save it. I saved it to the Colab storage, and then I copied this model to my Google Drive with the same name. And here, if you already have this file stored, this section allows to mount this model without further downloading. This is not a documented feature yet, so I found this in one of the PRs or issues to the LangChain project. That is transformers, sentence transformers package. Under the hood, by default, it looks for the model cached at this path. And that's why if we set this environment variable sentence transformers home equal to our path to the our Google Drive mounted, then we will be able to avoid this download. So, and we expect not to see this download progress bars. Okay, so it installed the needed packages and printed the embeddings model path, no download progress bars, so the model was mounted from the Google Drive. Next, we need to prepare our vectors storage, and in this project I used FAISS. Here in the LangChain documentation there is a list of supported vector stores. There are quite a few of them, and here is FAISS and the instruction how to use it. Again, in my project I generated the index, and then for subsequent runs I was mounting it from this Google Drive. That's why if we do not have it yet, we need to run this section once, and here we install the needed dependencies: FAISS for CPU, LangChain, and this LangChain wrapper for this vector store. Here we prepare HuggingFace embeddings, and to use the embeddings model from our storage, we again need to set the environment variable, which will define the path to our model, which is stored there already on the previous step. Here is the name which we will use for our index, JSProf's FAISS index 250. And here is the command, the line which generates vectors from our documents using the given embeddings model. And finally, we will save the ready index locally to the storage of this Colab, and we will copy it to the mounted Google Drive. I ran this earlier, it takes some time, so I won't run it again. And here is that index which I've got. So it's a folder with 2 files. If we have this index already, we can mount it. Let's do that. So again, I have some duplication in terms of installation of different dependencies because each of these sections can be run separately, individually. Again, here we are installing sentence transformers, and to use the needed embeddings model, we are setting the path to this model from our shared drive. We expect not to see those progress bars. Okay, we need to install FAISS. Right. And let's rerun this cell. Hugging face embeddings is not defined. Okay, so we mounted this index from our Google Drive, and now we are ready to test the similarity search. We will run this cell, and what it will do is it will use this method to look for this test query, and under the hood it will generate a vector for this query, and it will look for the closest vectors stored there, and it will return one top result. Here it is. We will print the page content. So the question was, what are constants? Declaring and initializing constants. So something which seems to be relevant. Metadata. It's our PDF file, page 167. Similarity score of this document is this value. Let's run it all together. For the sake of purity of the experiment, I will restart my Google Colab, reconnect to the runtime. Next, we will mount the Google Drive. Here is our mounted folder, and it contains the embeddings model, the face index with contexts, and the large language model. Next, we will run this cell. It installs the needed dependencies, imports the needed tools. Then we set a number of variables, that is the path to the embeddings model, which we will also set as an environment variable, the path to the large language generating model, and the path to our face index. Next, we will prepare our large language model, mount our face index, compose the prompt, prepare the large language model chain, and here is our example query which we will be using. What is a constant? Here we will look for relevant pieces of text in our vector database. And next we will run the chain using the query and the context. Here in the output we see that it mounted the embeddings model, the face index, and the LLM. So here we see the query, the context list, and the context contents, which will be suggested as the context for the question to be answered. And let's try how it responds to our question. And here's what we've got. Not very relevant. Let's try some other query. For example, let's ask, does JavaScript support multi-line comments? So we see the context which was retrieved and which we expect to see in the answer. So about single line comments and multi-line comments. And after around 2 minutes 20 seconds we've got this answer. It's not exactly correct, so multi-line comments with each line which starts and ends with double slashes is something in new. And actually I'm not sure if it's the context rephrased or whether it's a response from the model itself. And let's try one more example. For example, what's the difference between null and undefined? The context retrieved seems to be relevant. Let's see how it uses it for answering. And while we are waiting, let's try to ask our prompt to the model itself. So we will launch this GPT4ALL 7 billion parameter model locally, following the instructions from the official GitHub repo. Now let's construct our prompt. We will copy a piece of the context retrieved and fill in the question and the context. So I will copy this. I will revert the changes in the notebook and I will paste it here in the console. So the model is apologizing and saying that it can't respond. Okay, maybe let's simplify the prompt and remove extra new lines and shorten the context. I will write like respond to the question, what is the difference between null and undefined? And I will give a bit different context string. So this time we've got some relevant answer. However, I do not recognize our context in this response. Looks like it's the response from the model itself. So let's ask this question without the context. And really we are getting some relevant answer. So looks like our context was not used by the model. Our notebook is still processing this cell. And for comparison, let's try the same thing with OpenAI's big model DaVinci 003 using OpenAI's Playground. So I will write again the prompt respond to the question based on the context provided, and I will add the question and our context. So we're getting some relevant answer, but actually, to tell the truth, looks like it also may be the response from the model itself and not from the context which we've provided. Okay, and finally we've got the response from our notebook after around 5 minutes. And it's also relevant, but doesn't seem to be our context rephrased. So let's sum up. The good things. We were able to run this complete setup for context enhanced question answering locally using open source components. Similarity search, from my experience, is working quite nicely. both in terms of the quality of the output and in terms of the latency. So I didn't do special profound comparisons, but like subjectively, it feels like this setup using the HuggingFace Embeddings model and FAISS works at least as 80% of this setup I tested earlier with OpenAI Embeddings API and Pinecone. The GPT4ALL language generation model also performed not bad. So also especially taking into consideration the difference in the size in comparison with OpenAI's, for example, models, and that it's open source and it's run on CPU. The not so good things. The final outputs were not very good. Sometimes the model failed to respond. Often it seemed to ignore the context provided. It has quite small token limit, so we can't provide long context. And in general, when testing directly with on the model itself, even without this notebook, it may not work that good with prompts which include context and the question. And also the latency of this language generation on CPU is way too high. So from 2 to 5 minutes, which may work only for some experiments or POCs. So it's possible that GPT4ALL and similar models, given their size and the possibility to retrain on your drone data, they may suit better for retraining and not for generating answers based on the provided context. Well, also it's possible that this setup may be optimized. And lastly, taking into account how quickly these open source models are progressing, these results may improve in the nearest future. Hope that this video was useful. Please check the link to the Collab notebook in the description below.